Hey everyone, today we're going to be talking about how to find the area bounded by two curves. I'm going to start by just drawing a little example for us to chat through. That way we can just get an idea of what's going on. Say I have two curves, one that does something like this and another one that does something like this. And I want to find the area bounded or between these two curves. The first thing that we want to know is, well, where do these curves intersect? So we're worried about this point and this point. Say the point of intersection here, the x value is x equals a, and the point of intersection over here is x equals b. At this point, we should know or at least understand that if I were to integrate this top curve, maybe I'll call that curve f of x, I would get the area under that curve and bounded by the x-axis. So just to draw that in, I would get that entire blue area. If I were to then instead integrate the area under this red curve, maybe we'll call this one g of x. If I were to sketch that in, I'd be getting this red area underneath. So I don't want that whole blue area that I had drawn in before here, and I don't want just this red area underneath. I need just this pink in between. So essentially what I need to do is take that blue area and subtract the red area from it. If I were to write that with a nice integral expression, it would be the integral from x equals a to x equals b of the area from f of x or f of x dx minus the integral from a to b of g of x dx. We don't want to have to write two integrals every time, and we definitely don't want to have to write this much. So we combine it. We can just say the area that we are looking for is the integral from a to b of f of x minus g of x. Oftentimes you'll hear teachers, and I will refer to them today as the top curve and the bottom curve. So general idea here, we're going to integrate from the leftmost x value of intersection to the rightmost x value of intersection, the top curve minus the bottom curve, and that will allow us to find the area between these two curves. Let's look at an example. So first one that we're going to look at, we want to find the area of the region bounded by the graphs of y equals x squared plus x plus 2, y equals negative x equals 0, and x equals 1. First thing that we want to start with is some kind of a picture, right? I have to know what this looks like so I know what curve's on top, what curve's on the bottom, and the x values that I'm going to need to use for the bounds of my integral. I'm going to start with drawing y equals negative x first because that's just easier. Goes through the x-axis, has a slope of -1. Next, I'll put in my vertical line of x equals 1. And the last thing that I'm going to need is this parabola x squared plus x plus 2. So first thing, I know that curve passes through the point 0, 2. And on the line x equals 1, that's going to pass through 1, 4. So here's just a piece of that parabola, which is really all I need. Again, I'm looking for the area now bounded by x equals 0, so the y-axis, which is why I don't really care so much about what this parabola is doing when x is less than 0. This line, y equals negative x, my vertical line, x equals 0, and then that curve, x squared plus x plus 2. So this pink area is what I'm looking for. This is an easier example to start off with because it's pretty obvious what my furthest most left x values and right x values are to create the bounds on my integral. So I'm going to have the integral from 0 to 1, and then I'm going to take that top curve and subtract the bottom curve from it. So my top curve is the parabola x squared plus x plus 2, and then I need to subtract that bottom curve, negative x. I'm going to integrate this by hand because it's really pretty easy to do. So I have the integral from 0 to 1 of x squared minus minus. So I'm going to have plus 2x plus 2. When I integrate using polynomial integration, I get x cubed over 3 plus x squared plus 2x, and I'm evaluating this from 0 to 1. I plug in 1, so I have a third, plus 1 plus 2, minus, when you plug in the 0, it's just going to be a big 0. You get 3 and 1/3 for the area of the shaded region. Not so bad. Let's look at another one. Number 2, I'm looking for the area bounded by y equals 6 minus x squared and y equals x. Again, first thing I need to do is sketch this out and see what it looks like. So again, I know what curve is on top, what curve is on the bottom, and those x values that I'm going to need to use for the bounds of my integral. I know 6 minus x squared is going to be an upside down parabola with a vertex at 6. So that's easy enough to sketch out. And the line y equals x goes through something like that. So my points of concern are where the red and the blue are meeting, right here and here. Again, I'm not going to use a calculator for this one. Some examples you will absolutely need a calculator for, and some of them you will not. This one, you definitely don't need a calculator. In order to find these 2 points, I'm just going to have to set these two curves equal to each other so that I can solve for these x values of intersection. So I can say 6 minus x squared equals x. I end up with x squared plus x minus 6. I can factor that out. And I know that those x intersections are now x equals -3 and x equals 2. So this x value -3, this x value +2. When I set up my integral to find the area now, bounded by these two curves, I'm going to have that leftmost x value to the rightmost x value for my bound, so -3 to +2. And I'm going to do the top curve minus the bottom curve. So 6 minus x squared minus x dx. Again, I'm going to integrate this by hand. This really isn't so bad. I get 6x minus x cubed over 3 minus x squared over 2, evaluated from -3 to +2. Plug in the 2 first, minus plug in the -3. A little bit of arithmetic will get us to 20 and 5/6. Feel free to stick that in the calculator and double check, but I am fairly certain that is the answer you're going to get. Let's look at a couple more examples. All right, number 3, we're looking for the area of the region bounded by x equals 0 and the first intersection of y equals sine x and y equals cos x. Trig, everyone's least favorite thing to do. Okay, so when I sketch this out, I'll give myself some tick marks, pi over 2, pi, 3 pi over 2, 2 pi. I'll do y equals sine x first. So 0, 1, 0, -1, 0. And y equals cos x, 1, 0. Okay, so that first intersection point they're talking about is here, which we know between 0 and pi over 2, sine x is equal to cos x when x is pi over 4. So this pink region is what I'm looking for. That area is going to be the integral from 0 to pi over 4 of that top curve minus the bottom curve. The curve on top here is cosine x, and then on the bottom, I'm going to have minus sine x. Again, this is nice and easy to integrate by hand. I have sine x plus cos x evaluated from 0 to pi over 4. Sine of pi over 4 is rad 2 over 2. Cosine of pi over 4 is also rad 2 over 2. Minus sine of 0 is 0. And cosine of 0 is 1. So this is going to be 2 rad 2 over 2, or just rad 2 minus 1. There's that area. Not so bad again. All right, let's look at one last example. For number 4, we're looking for the area bounded by the graphs of 2x cubed minus x squared minus 14x and 4x minus x squared. This is more of an example that you would probably have a calculator for, just so that you can really see what's going on with these two graphs. I have an intersection point at x equals 0. I have another intersection point at x equals -3. And this last intersection point is at x equals +3. So this is the first one we're seeing where I have two separate areas kind of that I'm going to need to calculate in order to find the area of the region bounded by both of these graphs. And notice that from one section to the other, the curve that's on top switches, right? So I'm not going to be able to just do one integral to figure this out. I'm going to need two. The first integral I'm going to need is the integral from -3 to 0. So that's going to take care of this section of this red curve minus the blue curve. I'm going to let this blue curve be, this is the 4x minus x squared graph. So I'm going to call that graph F2. And this red graph I'll call F1. Just so that I can use them for shorthand. If you're going to put these in the calculator, you're going to want to keep track of which function is which so that you can write them down. So this first section from -3 to 0 is going to be f1 of x, the cubic function, minus f2 of x, that parabola. Plus, I still need the integral from 0 to +3 of the parabola, which we're calling f2, minus that cubic f1. So this second integral is going to calculate this shaded region for me so that I can get the area of both of them combined. You're definitely going to want to just stick this right in the calculator. Again, store the cubic function in f1, the parabola in f2, and if you're lucky enough to have the Inspire, Shift plus gives you that definite integral symbol, and then you can call upon these functions with the vars button, which is fantastic. When you stick all of that in, you get an area of 81. I hope you found this video helpful. If you have any questions or concerns or comments, please feel free to leave them in the comments below. Have a great day.